they just call it take-home exam. But so we'll just have that one take-home exam this semester, and then I guess we'll have the homeworks plus this other take-home exam.
So it'll be more than 50-50 as opposed to, because the syllabus and there'll be one.
Oh, yeah, I'll figure out how to kind of distribute the grading from the homeworks versus the take-home problems and whatnot. When I'm going through and taking a look at that, how much effort I guess went into the various things. You know, to kind of work out exactly how to do the grading. And then we'll see, how much time there is as far as if we want to try to, if there's other topics, kind of pick and choose a few topics to discuss in the lectures and so forth. So in this chapter then, I would say read through the section that you want to pay a little more attention to from a quantitative point of view is going to be section 13.6, which I decided to pick out a couple of problems which will deal with fusion for this one. So that'll be pretty much, I think, the last two problems that I have on the take-home final will be from this section right here. So you'll want to kind of read through that particular section. Well, I would say read the whole chapter more or less, but then put a little bit more focus on that section when you're going through and trying to understand things from a quantitative point of view. And so, at any rate, so I suppose you can kind of think of a nuclear reaction as being a little bit analogous to just a regular chemical reaction in chemistry. And the idea is that, well, you can actually combine different nuclei or particles together to form different constituents. And so, and the main thing, of course, is I think we're talking about energies that are sufficiently low. I mean, they're not exactly super low from the point of view of everyday life, but compared to what they do with the Large Hadron Collider, these would be really low energies. So what does that mean? That basically means that if the energies are low enough, the number of protons and neutrons will actually be conserved in the reaction. So in other words, we're not going to be sitting there smashing everything to smithereens into the quark constituents and creating these quark gluon plasmas or whatever, like they might be doing in the Large Hadron Collider. So that means if you look at this reaction right here, so how can you tell if those things are conserved? Well, if we take a look at this, just kind of remind yourself that this alpha particle is really the same thing as a helium-4 nucleus. So this guy has 2 protons and 2 neutrons. Now, the number of neutrons here, this is the total atomic mass, I guess, or it'd be, I guess, this would be Z. I think they call that, what is it? A, I think that's what they call it, the atomic number. But well, at any rate, one of these would be Z, maybe the other is A, but the idea is that this is the total number of nucleons, protons plus neutrons, and so that means the number of neutrons for this guy is 7. So this is the number of protons right here would be 7, and the number of neutrons is also 7. And so now if we say, okay, we're going to combine this plus this, can we see if the total number of neutrons and protons is indeed conserved? So if you look at this, okay, that means we have 7 plus 2 protons inside of here, so that gives you 9. Okay, well that actually does add up, because here we have 8 plus 1, which also gives you 9, so that means, okay, yeah, that's conserved. The number of protons is nicely conserved in this case. And now if we say, okay, but how many neutrons do we have right here? Okay, we have 17 minus 8, which is 9 neutrons. And you can see that actually adds up correctly, because here we have 14 minus 7, which is 7. 7 plus 2, because if 2 neutrons over here, it still gives you 9. And so it's not immediately obvious when you look at that, just glancing at it, until you go through and do a bit of arithmetic in your head, that you see, okay, yeah, the number of neutrons and the number of protons is conserved during that reaction. And now, of course, when you look at something like this, it's not at all obvious about, okay, is it going to, is it going to release energy, or is it going to absorb energy during this kind of process? And so that's when you have to take a look and see some of the details about, for example, if this has some finite binding energy, let's say compared to this guy right here. I suspect this may actually be a case where perhaps this may end up being more energetic in order to conserve energies if we actually go through, if this thing has some finite binding energy compared to whatever has been absorbed during this reaction right here. Now they have some other funny notations. I don't know if you necessarily need to get into bogged down in trying to follow these notations that they talk about, but one of the things that they'll do is they'll say, okay, they'll write, I guess they'll use a lowercase, I think, to represent the projectile. So in this case, the alpha particle might be x, for example. They'll use the uppercase to represent the target, let's say. And so this would be the bigger nucleus, so this would be the nitrogen nucleus right here, and then this would be the proton, that would be the oxygen nucleus right there. And so then as a shorthand, these might be a way of representing the two projectiles, and then these would, and X and Y, capital X and capital Y would represent the daughter, would represent the initial nucleus, and then the daughter nucleus right here would be the final product, I guess, nucleus right here. So that's kind of another shorthand that they sometimes use. And okay, this gives you some of the old things that were developed back in the 1930s in terms of, let's say the early, this would be like a very, very old version of the old cyclotron version of a particle accelerator. The idea is that if you go back to your 1322 class, you'll remember that if you just have a, let's say, an electric field going along some direction, so actually maybe I'll go into that's probably not a bad idea for me just to kind of draw a picture there. So if you go back to your 1321 class, let's see which way I want to do it. I guess I'll put the field coming like this. So let's say you have a field coming out of the board, and so now if you go back to your 1321 class, and let's say we have a particle that's could be either positive or negatively charged, but let's say, okay, for the sake of argument, let's suppose it's some maybe a positively charged particle. In which case, I think. So if you go, so if you remember that no, I'm sorry, I think I want the field to be going into the board like this, because if you remember, you do your.
So the circled dot is
the force acting on this guy is, which I wanted to draw it a little bit better. So at any rate, the force acting on this guy is going to be QV cross B from your 1322 class. And so that means that if B was going into the board and V was going this way, if it was a positively charged particle, so if it was like an E plus, either proton or positron moving that way, then the force would be going toward the center of curvature in that case. And then of course what's happening is that that force keeps changing because the velocity keeps changing. So this, so you get this cyclotron motion. And so if you go back to your 1321 class, so let's suppose that Q is equal to E. And by the way, everything's perpendicular, so the magnitude is just EVB. And then if you set that equal to MA, just again going back to your 1321 class, that would be M times, remember your centripetal force is going to be V squared over the radius of curvature. And so that means that we find that we have, what is that, EV is equal to MV over R. Or we can say, let me write it like this, EV over M is equal to V over R. And I'm going to remind you that if you divide the linear velocity divided by the radius of curvature of motion, that's equal to the angular speed, essentially, which is essentially the frequency at which this thing is rotating around. And so, therefore, you can see that the cyclotron frequency is going to be E B over M, essentially, whatever the mass is. And if it's, assuming that the charge is E of your particle. Now, if we, now that's the problem is, of course, that doesn't really give you a way of accelerating the particle if you just have just a simple constant magnetic field. So how would you go about accelerating a particle and then still somehow maintaining or basically getting this thing to go up to higher and higher speeds? Now, of course, if you keep going to higher and higher speeds, in the old original cyclotron, the radius of curvature will keep increasing, because if we go do a bit of algebra, well, this, I think this remains constant, but as V goes up, R goes up, essentially. So what they did then is they said, well, let's split this up like this into regions where we not only apply a magnetic field, so I think you would still have your magnetic field going like this, but what we will now do is we'll have a voltage, and I think what you want to do is you want to tune that so that it's equal to the same frequency. So this will be operating at the cyclotron frequency. And so then what happens is that your particle might start out, and you have to have, I guess you also have to have a way of injecting the particle in as well. But the idea is that, okay, once you set up this kind of configuration, if you have a way of injecting the particles, each time it goes through, you time your voltage such that it's, as it goes across this gap, it's going through a potential, basically, a potential difference. So each time it goes across the gap, the thing gets accelerated. And and now what happens, of course, the problem is that the radius of curvature keeps getting bigger and bigger until finally it exceeds the radius, so then it kind of leaves, and I guess you're able to create a beam coming out somewhere. And so this is the old cyclotron. Now, what people, of course, it's kind of inconvenient because the problem is that the radius of curvature keeps increasing, and you're kind of limited because eventually you can't keep having it confined to a single path multiple times. And so in order to correct or to compensate, that was built here way back in 1932, in order to compensate for where to try to avoid having to go have this radius of curvature constantly increasing, they developed what they call the synchrotron. And so I think what they did, and so the synchrotron, I think, is designed where I think they will, I'm not sure if they do some fine tuning of this frequency or exactly how they do it, but they are able to confine it to a single circular path. And so all the more advanced particles, and of course you also have to compensate for relativistic effects that become very enormous. So when you really accelerate these to high energies, you get up to like 0.99% of the speed of light or whatever, or 99.9 something percent of the speed of light, then the relativistic effects are huge. And so all of the modern particle accelerators, like the Large Hadron Collider and so forth, are synchrotrons where you would actually confine the particle. In the Large Hadron Collider, it goes through several stages. So it'd be like a smaller synchrotron, you have a beam coming out going into a bigger ring, and then finally I think it'd be the biggest ring, which is whatever, 21 kilometers in circumference or whatever that is for the Large Hadron Collider. So it'd be a single path, and then of course the idea is that you don't need this humongous D magnet, because you would want something like that to be 20-something, or 7 kilometers in diameter, or 27 kilometers in circumference. So what they do is they have single, or they confine it within this path, or this tube, basically, using these something like 11, I think it's 11 Tesla superconducting, or maybe it's 8 Tesla, I forget the number, but superconducting magnets that are specially designed so you can confine the particles to a single path. And then, remarkably, I think they're able to have particles of the same charge moving in opposite direction in a very clever way, but by mechanisms which I completely slipped my mind, on how they can have two particles of the same charge in other words, the same sign of charge going in opposite direction, yet bending in the same direction. So there's a lot of tricks that go into how they actually design something like the Large Hadron Collider. So here they talk about, okay, different possible types of reactions. This would be the least interesting right here, where you just have things that are completely scattered without actually creating any particular products involved, and so you're not really absorbing or emitting or releasing energy in the process. But the inelastic ones are the ones that, of course, would be more interesting from the point of view of, let's say, either neutron capture or fusion or fission and so forth. So this is something that I decided I probably, well, I don't have any exam problems talking about this. You kind of look through, at least try to get a qualitative understanding of cross-section, but the idea is this is a way of characterizing what is the, in other words, how likely is it for you to scatter something off of a target under different circumstances. And so this is used a lot. We use it, or one of my colleagues uses it in the technique called Rutherford backscattering spectroscopy, where the idea is that a lot of times what you're doing is you have a beam of, it could be alpha particles, or it could be any number of different types of particles that might be coming down, and several MeV, or the energy in some cases, coming in and hitting a solid target. It could be a sheet of superconductor or any number of things that you might be looking at. And typically what you're doing is you're scattering them off the nuclei, which have a very tiny cross-section typically compared to the surrounding electron clouds, but because they have a harder shell and a stronger interaction, that's actually one of the dominant mechanisms by which you actually see scattering taking place. And in the early days, when Rutherford was actually doing some of the experiments to show that atoms are in fact composed of a nucleus surrounded by an electron, where the nucleus is very tiny compared to the overall size of the atom, it was these types of scattering measurements that actually kind of showed that, because the idea is that if it was just a big blob, you would expect that when you have your beam coming down in, let's say, certain directions, then you might have some smeared out probability that the thing was scattered. And then what he actually discovered was that when he took like a very thin sheet of gold as an example, because he bombards it with something, whatever it was, like protons or whatever that was he was using. Well, what happened was rather kind of interesting at that time. In other words, and not everybody expected that this would be observed, but what he found is that a lot of times these particles would just go straight through the sheet of gold. Nothing happens, pretty much. It just goes right through, zips right through. And then other times it would go down, and then boom, it just like completely backscatters off of something. And so that was an indication that you had something that had a very hard shell, but a very tiny cross-section was the idea. And so that was one of the strongest pieces of evidence for initially at that time, for the existence of the nucleus. It was actually Rutherford that actually made some of those important discoveries. And so this method then of characterizing cross-sections is good to kind of have some, at least semi-quantitative or qualitative understanding about that, although I'm not going to give you any take-home final problems that go into some of these details, but if some of you end up working, let's say, with Professor Wk11of, that would be something you'd really get into a lot of the details, the gory details about that. Okay, so now getting into a little bit about reaction kinematics. Everything is relativistic in the sense that what ends up happening is that, so let's see here, I guess in this case we could think of the big X as being our initial constituent, or reactant, I guess you'd call it, reactant right here. And this would be our initial, let's say, a small particle that we're coming in, and maybe that we're bombarding the reactant with, or the nucleus with right here. And so we assume that maybe this guy is sitting at rest right here. And so if this guy is sitting at rest, we assume that, okay, whatever energy is bound up in this guy could be characterized as whatever this mass is. If you just measure that mass times just mc squared, that's it. So we're assuming that this doesn't have any additional kinetic energy right here, and that all your initial kinetic energy is in the form of your, whatever it is you're using to bombard it with. So this could be an alpha particle right here. So it has this amount of rest energy, that'd be your kinetic energy. And now, okay, after the reaction, what happens in general would be that you may have two small particles coming off. So maybe, okay, maybe this guy right here might have been let's say an alpha particle right here. Maybe this guy was our neutron nucleus right here. I'm sorry, our nitrogen nucleus right here. And then maybe this guy right here was the proton right here coming off. And now, okay, we say this guy has some finite kinetic energy of the proton that's been scattered or created after this reaction. And in general, we might say, okay, that whatever was created after the reaction, so in this case, this might have been oxygen, I guess oxygen 17, if I remember correctly. So this could be oxygen right here. So it has this rest fast energy, but again, in general, to conserve energy, it might have, it'll very likely end up having a certain amount of kinetic energy in addition to having a slightly different mass. In other words, again, the masses do not add up in the normal way simply because we have that extra mc squared energy difference, which all might be associated with the binding energy, which could be like several MeV worth of energy, or binding energy involved in creating that oxygen 17 nucleus in that case. And so you end up with with a certain amount of kinetic energy that's released in both the small particle and then the daughter nucleus that's created during the reaction. So then what they've done is they've said, okay, I guess this binding or disintegration energy, I guess depending on how you look at it, in other words, the energy difference between the initial basically, exactly. So in other words, the energy difference between the initial energy of these constituents and the energy involved of the, let's say, the daughter constituents right here, are going to, so that's your difference in mc squared energies essentially, right there, are then going to be released. Well, some of it's going to be absorbed by this kinetic energy here, but then the rest is going to be released in the form of these two kinetic energy terms right here. And so just using energy conservation and including the fact that the mc squared energies just do not exactly add up. And so that's what gives you that extra kinetic energy, which is going to be this guy right here. And so what I guess what the people have done historically is that we'll define this difference in energy as being the Q value in that case. And so the idea then is that if Q is greater than 0, that means that this guy releases energy. So in other words, exactly. So we have an exothermic reaction, or they call it exoergic or exothermic, either way, reaction. And so that means you're going to have a finite amount of kinetic energy that's going to be released during that reaction. That would be the kind later, I guess if we talk about fission, where you may, instead of having this guy be a little tiny, or fusion, maybe probably might be a better example, where instead of this guy being a little tiny particle that's bombarding your nucleus, if you actually have two nuclei which are combining to form a new, larger nucleus, the idea is that you want this to be positive right here in order to be able to release the energy during the fusion reaction, assuming that you want to get energy out of that. You actually want to use that, let's say, to produce energy, or you're trying to understand, okay, how does the star actually able to eventually produce enough energy to give off the amount of light that a star gives off, and so forth. And so, at any rate, the opposite would be the case if Q is less than 0. Then we say that that's an endoergic or endothermic reaction. And then finally, elastic collisions would be a case where Q is exactly equal to 0. And so the idea then is that in the case of an endothermic or endoergic reaction, that means that this guy, there's going to be some the absolute minimum energy required for your bombarding particle coming in that's going to be needed is going to correspond to the case when these two guys are exactly, I guess, presumably equal to 0. And so if you do some algebra, then I guess you would find that, and then using the definition for Q, in that case, you would find, okay, that this minimum energy would be the thing that would be needed, I guess, or yeah, so if Q was less than 0, for example, and Q is actually negative, then you'd actually find, okay, this will actually be a positive number. That threshold would be the minimum amount of energy from this guy to come in and be able to allow that reaction to take place. Now, it's interesting also, I should point out, this is actually kind of interesting in the context, which I hope will make sense when we get into fusion, if we think of these as being nuclei instead of just being bombarding particles, because in the case of fusion in a star, like a very massive star in particular, what's going to happen is that I remember I showed you that plot last time, or one of the earlier lectures, talking about the plot of the binding energy of a nucleus as a function of the different nuclei. And so when you finally got to iron, so it peaked right around iron, and that's what started to tail off, and so you start to no longer really, it's no longer advantageous to have a fusion reaction once you get above iron. And so what happens is that for anything heavier than iron, Q becomes negative. And so that is when the star is in its death throes. In other words, once iron starts to fuse and these try to fuse to form heavier things, it's absorbing energy instead of releasing energy. And so that's when the interior, or the star, basically starts to collapse in on itself and form either a black hole or a neutron star, and then the outer part just blows out in